don't get tired from it, please, because it's a very simple one. It's a very basic one. So, but it's a basic foundation for understanding a neural network. We can use also, in fact, you can use it also for making something very nice. You have here the link for the lecture. I will post it also to our Blackboard, so we are sure that we have it. Maybe I will do it after lecture. I will put it in Blackboard after our lecture. So at the moment, I will just keep it here. Yes. So our lecture today, in fact, it's about perceptron and perceptron learning rule. And this perceptron, it's very basic. It's a very basic and very simple tool. This is a basic unit in artificial neural network. Artificial neural network, in fact, it consists of layers, and in each layer contains some perceptrons or neurons, and we can build complex models if we can use this multi-layer perceptron. They call it multi-layer perceptron, MLP, multi-layer perceptrons. So multi-layer perceptrons, it's layers of perceptrons, and it's multi-layer, so we can build more complex models. But this multi-layer perceptrons consists of perceptrons, and each perceptron, in fact, is very efficient, right? So we can see this perceptron. Okay. So today we will talk about a perceptron, which is a basic unit. And if we need to draw this perceptron, the perceptron, it's like a circle, and this circle has number of inputs. Those inputs will be your features, right? And we will take weighted sum. So we will take the weighted sum of those inputs. So we have some inputs. I will call it, for example, x1, maybe x2, maybe x3, maybe like iris dataset. If you remember it from last time, iris datasets, we have 4 inputs, right? So I will play with iris. So we have another x4, and each input is connected with the perceptron with a weight value. So this one, it could be omega 1, omega 2, maybe omega 3, omega 4. So we will take the output from this one. It will be just weighted sum. So it will be omega x, summation of omega x, omega I, xi, I equal 1 to 4, correct? So it will be something like this one. So we will calculate this weighted sum. And after calculating this weighted sum, we will apply it. It will be a number, right? We will apply this number to an activation function, right? So it will be a number. So if this number is greater than 0, you can say that the output is +1. Otherwise, the output will be 0, for example. So in this case, we can use this one for binary classification problem. Perceptron is used only for binary classification problem. It can be used also for regression, in fact. So, for example, in iris dataset, we have 2 species, Setosa and versicolor. So I will use the 4 features, x1, x2, x3, x4, to classify if this species is Setosa or versicolor. If it is Setosa, it will be 1. If it is versicolor, it will be 0, for example. So it's binary classification problem. How will we do this? It's just very, very easy. We will have those features, input features, x1, x2, x3, x4. We will feed it to my model. We will have the weighted sum of those features using omega 1, omega 2, omega 3, omega 4. Those omega 1, omega 2, omega 3, omega 4, you can select it by trial and error, for example. So we will say, okay, I feel that x1 is very important, so I will put omega 1 equal 0.8. Maybe x2 is not very, very important, so I will reduce this number. I will make it maybe 0.1, and so on. So you will assign numbers to those weight values. You will have this weighted sum. And after that, I will get a number, scalar number, because omega multiplied by x summation, you will get a number. Maybe this number is 3.5. Okay, we will apply this 3.5 to my activation function. So 3.5, it will be a number here. So in this case, okay, the output will be 1. So in this case, we will say that, okay, this species is Setosa. For another 4 features, maybe it's a versicolor, we will get different set of numbers multiplied by the weights. Maybe we will get a number which is less than 0. Maybe it will be, for example, minus 0.5. Okay, now minus 0.5, it will be converted into 0, and 0 means this species is versicolor. So in this case, we can use a perceptron for solving binary classification problem. How can we find omega 1, omega 2, omega 3, omega 4? We will find it, in fact, by training. We will learn from data, and we will try to find a good combination of numbers, which will give us good accuracy. Maybe you will be happy if you can get accuracy maybe 90%. So we will train the model. We will adjust omega 1, omega 2, omega 3, omega 4 until we will keep this one in iterative approach until we have good accuracy. Maybe it's accuracy 90%, 95%, and so on. So today we will talk about a perceptron, right? This is the basic structure of a perceptron. And if you want to adjust the weights, we have very nice rule called the perceptron learning rule. So we will talk about this perceptron learning rule. This perceptron learning rule, it will help you to adjust the weights automatically from data by learning, right? And after that, we will talk about something called adaptive linear unit. It's also a perceptron, but this perceptron, it has linear activation function. It is used for regression, because this, you see here, this activation function, it's like step activation function. So it is used for classification problem. But if you want to use regression, we can just a linear activation function, right? So it means the output will be the output from this summation. So I want to predict my income next year based on my age. Maybe X1 is my age, X2 is my years of experience, maybe X3 is, I don't know, something else, my height, maybe X4, it's my weight. So based on those features, I want to build a model to predict my next salary, my salary next year. So in this case, I need to make regression. I need to regress a number. So maybe it's enough to just have it as weighted sum, right? If age is important, omega 1 will be a very large number. If weight is not relevant, right? If obese people, they will get less salary for some reason, right? Maybe this number will be high. If weight does not make sense, so omega 4 will be very small number, right? And so on. So maybe it's appearance. Maybe I need taller people. So in this case, height will be important. So in this case, omega 3 will be high. So in this case, anyway, we can use this perceptron for classification problems, and we can use it also for solving regression problems. We need to talk about feature scaling, some maybe feature scaling techniques. Maybe next week also we will talk about data augmentation, because data augmentation is very important technique. Usually people are working with a small set of data and they want to expand the size of the data set. So maybe next week I will talk about data augmentation techniques. How can we expand the size of your data sets? And at the end, we will have some examples. So let us start with the perceptron. So the perceptron, it's the basic unit of artificial neuron. This is the basic unit, because as I told you, if you want to build a multi-layer perceptron, it will be a layer, and this layer will consist of number of perceptrons. So it could be something like this one, right? So it could be like, we have here my inputs, right? X1, X2, X3, and X4, for example, and we have those connections, and at the end we will make some classification problem. So in fact, MLB, it consists of, it's called the multi-layer perceptron. It's multiple layers. So we have multiple layers. Maybe I have two hidden layers, one output layer, and each layer consists of number of perceptrons. So this perceptron is the basic unit of artificial neural network. If we can understand the perceptron very well, we will understand all the rest. The rest will be easy because it's just the extension or expansion of it. The perceptron can classify a task into two classes: be positive, negative, yes, no. So it's a binary classification. So if I have a data set and I need to classify into cats and dogs, I did very simple example to elementary school students. So I told them we have a house called the cat, it's called the dog's hotel. In this dog's hotel, we need to use artificial intelligence to classify animals into dogs and the cats. And the door will open only for dogs, not cats, for example. So in this case, it's a binary classification problem. We just need to take an image of the object or the animal, for example, and we need to classify it into dogs and the cats. So it's a binary classification problem. When it is dog, it will provide me with 1. When it is a cat, it will provide me with a 0. Of course, there are some cases where we can be confused because there are some very small dogs and some large cats. So maybe when the animal is, it's a very large cat, maybe it will be misclassified as a dog. And then when the dog is very small and beautiful, maybe it will be misclassified as as a cat. It could be. So there are some cases where we will be confused. So this decision function can be defined as a linear combination of input values, which is xi. So those xi's are input features. So it could be the height, weight, last salary, correct, eye color, correct, stuff like this. And the corresponding weight values. We have those weight values, those omega i's. Those omega corresponding weight values, it will reflect the individual importance of each individual feature. Some features are more important than the rest. So how the model will decide this? It will decide this by selecting higher values of omega or small values of omega, right? It could be positive value, negative value, because it's proportional. It's proportional to this or inversely proportional to this. So it's according to this weight value or absolute value of weight, it will reflect the importance of this feature. For example, I want to predict my salary next year, so maybe my salary this year is very important. So in this case, omega, which is connected to my current salary, will be very high because this is important factor in deciding your income next year, for example. Years of education, maybe, is it important or not? Years of experience, is it important? But maybe nationality, maybe the nationality is not important. So the weight value, which is connected to nationality, will be very, very small, right? So, and so on. So we will get this decision value. We will get this net value. This net value, it will be the weighted sum of inputs. So it will be, in fact, the summation of omega I multiplied by xi and I equal 1 to n or m plus something called the B bias. So it will be like this one. So it will be omega 1 multiplied by x1 and so on plus omega m multiplied by xm plus something called the bias. So if you want to write it as a matrix multiplication in matrix notation, so it will be omega transpose multiplied by x plus b. If you want to write it in more details, it will be like this one, because this one, it will be a vector of weights. So it will be here omega 1, omega 2, omega n multiplied by this features x1, x2, xn, correct? So it will be like this one. So if you want to write it in matrix notation, it should be omega transpose x plus b. Just remember to add here p plus b. So it will be like this one. So it's just weighted sum. It's a linear combination of inputs or weighted sum of inputs. Inputs are input features. Just remember iris datasets. We have 4 features: cetus length and width, and sorry, it's petal and petal length width and length and width, and the sepal length and width. So those are the 4 features which we use to classify each one. So we will calculate this net value, and after calculating this net value, we will apply this net value to an activation function. This activation function, it will convert this value into 2 numbers, maybe +1 and a -1, right? Or +1 and a 0. So in our example here, it's a +1 and a -1, which means the activation function will be something like this one. So this one, -1, +1, which means +1 will be converted into +1, +2 will be converted into -1. So now we can solve binary classification problem, right? So if you want to write it in one line, so it will be you can say that f of x will be, for example, will be just f of net. For example, it will be just omega x plus b. It will be like this one. So the value here, in fact, it will be like maybe +1 and a -1. Very easy, omega x plus b. So this is one perceptron. In fact, if you want to convert this perceptron into a full layer, you just need to expand this omega transpose. This one should be a matrix, not a vector. If this one will be a matrix, it will be one layer, right? So okay, so step by step, because I don't want to make. So we have here weights and the bias. Those weights, it causes the rotation of the decision line. We have a decision line if you have 2 classes. In fact, our model will draw a line. This line should divide my classes, my data, into 2 different classes, class A and the class B, for example. To control this decision line, those omega values, it will cause rotation. It will make my line rotate. If you change it omega 1, omega 2, for example, it will rotate my line, and you have a bias value. This bias, it will cause translation of the line. So if I need to shift the line up and down or left and right, I need to change the bias value. So weights will make the line rotate, and the bias will make the line move up and down, left and right. So if you want to make it, imagine that you have a data set, and this data set, as you can see here, we have those red circles and white circles, and we need to classify it. So I need to have a model. My model will draw a line because it's a linear classifier. So it will draw a line, and we can just say that all data points above the line will be classified into 1, and all data points below the line, it will be classified into -1, right? So now we have two classes. We will label class A by 1. We will label class B by -1. So how can we do this? So my data, if you can see here, my data points are represented by two values, X value and Y value. So as you can see here, this is maybe X1 and Y1. So in fact, this is X and this is Y. So each feature is represented by two values. So if we can say that, okay, my data set will be like this one. So X, Y, maybe Z will be the output. So I have some red points. So this one, it's a red point. This one, it's white point. When it is red point, we need the output to be +1. When it is white, we need the output to be -1, right? And I have X and Y are coordinates. So we have some coordinates. So we want to say that, okay, we need all data points which are located above the line to be classified into +1, and all data points which are below the line, it will be classified into -1. How can we do this? Simply, we just need to build a very simple model. So my model will have two inputs. Those two inputs will be X and Y, and we will take weighted sum of the inputs, and we need to apply this weighted sum to an activation function. This activation function will be symmetric, not step, it will be symmetric like this one. So the output could be +1 or it could be -1. So we have here output, I will call it Z for example. So in this case, each data point will be classified to either +1 or -1. If X and Y are located above the line, it will be +1. If X and Y located below the line, it will be classified into -1. If you change it ω1 and ω2, it will rotate the line. So the line will rotate, right? Because ω1 and ω2, it will control the slope of the line. So changing ω1 and ω2, the line will rotate. We have something here also called the bias. This one. So the weight to the bias, it's just +1. We have another factor, P. If B equals 0, it means this line will go through the origin. If you change the B value, maybe the line will go up and down, correct? Because in fact, the bias, it's the intersection with the y-axis. This bias value, it's the y-intercept, right? Because if you want to write this decision line, the equation of this decision line, it will be ω1x plus ω2y plus b equals 0, in fact. So this is the equation, in fact. So if you change it ω1 and ω2, the line will rotate. If you change the bias, the y-intercept will change. This one, it's y-intercept. So if b equals 0, the line will go through the origin. If it is positive, it will go up and down. Positive, negative, so the line will go up and down. So it's just to give you more degrees of freedom, because I don't know how my dataset is positioned in my X and Y, XY plane, for example. I don't know. Maybe it is to the top or bottom, I don't know. So if you limit yourself, if you set B equals 0, this line, decision line, must go through the origin, and what is left for you is only ω1 and ω2 to change. So you will be able to change the slope of the line, but you will not be able to shift the line up and down. So when we train the model, we just try to select a good combination of weights and the bias. We need to select a good value for ω1, ω2, and B, so we can have a good line. This line will be able to classify my data correctly with high accuracy. Because I can select a line which has an accuracy of maybe 70% or 50%. I can, if the two classes are overlapping, it will be really very difficult to achieve good accuracy, right? Because if they are too much overlapping, it will be difficult anyway. So it will be difficult even for a human to classify. So this artificial neuron, it's inspired by this biological neuron, as you can see here. So it consists of some inputs. Those inputs are connected with the cell body, with dendrites. It's like our mathematical form. So we have here this cell body, and this cell body has connections, and those connections are transmitting signals to the cell body, and it will make decision, and it will transfer the decision to another connection, to something else. So in fact, it's inspired by this biological model. But in human body, we have chemicals, we have hormones and some other stuff which are responsible of transmitting signals. So we will have those connections. It will try to sense things, and it will transmit it to the cell, and the cell will make decision, and it will send this decision to another cell, and so on. So this is how it works in our body. So now we need to start by simple model. We need to develop a perceptron which can classify a logic gate, and OR and XOR, for example. So how can we do it? So this is, for example, we can start with a very simple model like OR, this one. In OR gate, we have two inputs and we have one output, right? And if you can see here, we have two inputs, X1 and X2, and it's 0, 1, 0, 1, 0, all possible combinations of inputs, 0, 1, 0, 1, 0, 0, 1, 1. If you want to draw it in XY coordinates, it will be like this one. When it is 0 and 0, it will be 0. I will make it white, right? When it is 1 and 0, so this is 1 and 0. So X1 is 1, and this is, I will call this one X1. This one, it's X2. So I will have here another one. I will make it red. So this one, in fact, it's 1. The output here should be 1. When it is 0 and 1, so X1 is 0 and X2 is 1, so it will be something here, right? It will be like this one, another point. 1 and 1, so it will be 1 and 1. Both X1 and X2 are 1s, so it will be like this one. So this is, in fact, OR data set, right? So this one, I will label this one with 1, this one with 1, this one with 1, this one will be 0. Can you draw a line to classify it, this problem? If we need to classify it, we have two classes here. We have two inputs, and we have 4 examples. One example is classified as 0, and the 3 examples are classified as 1. Can you build a model to classify it? This is OR gate. Do you remember how it looks like? It was like something like this one, I guess. Like this one. We have here X1 and X2, and this is the output, Y or T, for example. So when X1 is 0, X2 is 0, the output should be 0. When they are different, the output will be 1. When both inputs are 1, the output will be 1. So this is my OR gate. Can you try to find how can we classify it using linear classifier? We need to draw a line, right? Okay. Maybe we can select, maybe the model will be something like this one. I can draw a line like this one. Okay, this line will be very good. So this is my model, right? If I need to build a model to classify it, so my model, in fact, will draw a line. So this line will be very good model. So this is my model, right? And we can just say that all data points which are located above the line will be classified into +1, and all data points below the line, it will be classified into 0. So in this case, I need to generate this line. How can we generate this line? Using a perceptron. The perceptron will be able to do this. So we just need to draw a perceptron, and this perceptron will has 2 inputs, X1 and X2, and we will take weighted sum, and we need to select an activation function. This activation function, what activation function we need to use here? Can you expect? Step, symmetric? Can you select, please?
Step.
A step function, yeah, this is very good. It must be step function, because step function, it will provide this 1 and 0. But if we will use symmetric, it will be 1 and -1. So we need to use this activation function. This is very good, because this one, it will help us to get outputs between 0 and +1. This is very good. So now we have the output here. I will call the output Y, for example. So the output will be like this one. Do you think this model is correct now? We will have here ω1 and ω2. Do you think this model will be able to generate this line? Are we missing something?
Missing the bias.
Yeah, very good.
Yeah.
Yeah, we are missing the bias, because without the bias, in fact, this line will go through the origin. It will be here without this one for b equals 0. So without bias, your line will go through the origin. So it will not be good, in fact, because if it will classify, because all data points above the line, it will be classified into 1. Maybe all data points which are located on the line or below the line, it could be classified into 0. So maybe it will be okay. But if you got some noise, because sometimes we are getting x1 and x2, we will get it from another device. Maybe there will be some noise added to it. Right, some little noise, maybe. So in this case, it will change the value of x1 and x2 a little bit. So in this case, it will be misclassified. So my model will not work, in fact. So in this case, we need to be sure. So in this case, it will be smart to select a line maybe in the middle between. So it should go through maybe this point, 0.5, maybe 0.5. It should be like this. So in this case, we need to add the bias. So this one will be the bias. So in this case, if we need to write an equation for this, the decision line, it will be net, because the output from here we call it net. So it will be like net equal omega 1 x1 plus omega 2 x2 plus p equal 0, in fact. All data points which are located on the line, it will generate 0. All data points above the line, it will generate 1. And all data points below the line, it will generate also 0. Do you want to test it? Can you select values for omega 1 and omega 2? Yes. So okay, step by step, we can select omega 1 and omega 2 maybe by trial and error, or you can try to relate it to this intersect 0.5, 0.5, because this is coordinates. So once we select the value for omega 1 and omega 2, we can substitute the value of x1 and x2 for this point. We will find that, okay, this is positive. It will generate positive value. And when we send this positive value to this activation function, it will be converted into +1. And if you have a point on the line or below the line, and when you substitute it in this equation, it will generate a negative value or 0. And in this case, it will be classified into 0. So in this case, we will be able to classify this data set into this one. And the gate, it is the same, but it will be a little bit different, right? So the AND gate, it's 0, 0, 0, 1. So it will be just similar to this problem, but it will be a little bit different, right? And we have the problem here in XOR data, right? XOR data point. When we need to look into this XOR, I will plot it here. So imagine that this one is x1, this one is x2. So XOR, in fact, it's 0, 0. It will give you 0. So I will have a point here. 1, 0. It will give you 1. So I will put it here. So this one will be green. So it will be like this one. And another point here, which is 0, 1 and 1, 0. We will have another point here. So in fact, I will write the coordinates. So the coordinates of this point, it will be 1, 1. Coordinates here, it will be 1, 0. And this one will be 0, 1. Coordinate of this point, it will be 0, 0. So as you can see, it's complex data set. We have two classes. This one will be the green one, it will be 1 and 1. Label, this one label here, it will be 0. This one will be 0. If you try to draw a line, it's complex, because we need to draw a line. I mean, if we will use linear classifier, we need to draw only one line, right? Only one line to solve this problem. So if I select a line, maybe I will draw a line like this one. What do you think about this line? Is it good? No, it's not good, because it will classify maybe one point correctly, the other point correctly, because this one will be classified correctly, this one will be classified correctly, this one will not be correctly classified, this one will not be correctly classified. So if I will use this line, red line, in fact, I will have 2 points correctly classified, 2 points wrongly classified. So the accuracy of this model will be 50%, because it's a 2 divided by 4. So the accuracy will be 50%. If you want to select another line, maybe I can select another line like maybe this line, this yellow one. Is it good? It's the same problem. Maybe this line will be correctly classified. This one will be wrongly classified. This one will be correctly classified. This one will be wrongly classified. So the accuracy also will be 50%. Maybe I can select this line here. below, I will draw it one more time here. Sorry, no. So I will select maybe this line here. So in fact, for this line, I will have this one correctly classified, this one correctly, this one wrongly, this one correctly. So the accuracy here will be 75%, right? So you will not be able to achieve 100% with a single line. So and this specific problem, this problem has a big history, in fact, in artificial intelligence, because once they invented this perceptron in 1940, they discovered that a perceptron cannot solve XOR problem. And after this problem, we got this, they call it AI winter. People lost interest and lost trust in AI developers at that time. Because once they discovered this perceptron, they said, okay, we have a perceptron and it's a smart model and it can classify any problem. And once they tried to solve a simple problem like XOR, they found that it's impossible to solve, right? It's impossible. So I need to add one slide here, so I just can explain it in more details. So sorry for this. So one more time for this XOR problem. Sorry. This XOR problem, it's like this one. We have two inputs, X1 and X2, 0, 1, 0, 1, 0, 0, 1, 1. And the output here, it will be 0, 1, 1, 0. And then when we draw it in XY coordinates, we have here X1 and X2. It will be like this one. And this one is square. So we have two different classes. So this is our problem, right? So we have this problem, and we need to find a line which will classify it. So as I told you, if you will select a line like this one, the accuracy will be 50%. No, this one will be 75% accuracy, because this one will be correctly classified, this one correct, this one correct, this one wrongly classified. But you will not be able to achieve 100% accuracy. If you want to achieve 100% accuracy, you need to have at least 2 lines, right? You need to have 2 lines like this one. We need to add 2 lines. So my model should consist of 2 lines. And in this case, we will say that all data points between the 2 lines will be classified into +1. And all data points above or below, it will be classified into 0. This one will be classified into 0. This one will be classified into 0. So in this case, in fact, we can reach an accuracy of 100%. But now my model has 2 lines, so I need to use 2 perceptrons. So I will draw it like this one. I will have one perceptron, another perceptron. The inputs to the 2 perceptrons will be X1 and X2. Can you see? So this one X1, this one X2. We have here bias B1. We have another bias here B2. In fact, this model, this model will generate this line, and this one will generate this line. So now I can generate 2 lines, right? But also I cannot use this one because it needs manual work, because I will get a number here and I get a number here, and I need to sort those numbers and decide if it is 1 or 0. To solve this problem, we need to add another perceptron here. So we will add another perceptron here, and this perceptron will make the decision. So at the end, I will get a final decision, which is +1 and 0. If you look into this simple model, it's multi-layer perceptron, right? This model in front of you, it's MLP. Multi-layer, because in fact here we have 2 layers. We have input layer. This one we will call it input layer. This one here in the middle, we will call it its hidden layer. And in fact, we have an output layer. So to solve this this XOR problem, it's impossible. You cannot solve it using a perceptron, but you need to develop something more complex, right? We need to use more complex model. This complex model, it will consist of MLP. So in fact, the first step after they developed this perceptron, they developed the multi-layer perceptron. But it was a big problem, because if I want to train my perceptron, I can use MLP. I can use this perceptron learning rule, which is very easy rule to modify weights and adjust it. But if you want to train this model, multi-layer perceptron, MLP will not, this perceptron learning rule will not work with us, because this model has many weights. So this one has omega 1, 1. I will call it omega 1, 1. This one omega 2, 1. this one omega 1, 2, this one omega 2, 2, and after that I will have another weight here V1, V2. We have here B1, B2, and a bias here B3. So this model has 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9 parameters. This model has 9 parameters. But in case of a perceptron, it was much simpler. It has only 3 parameters, omega 1, omega 2, and bias. So to solve this XOR problem, you need to build a multi-layer perceptron. And the multi-layer perceptron, you need a different technique to train it, in fact. And they couldn't achieve this before getting error bag propagation in 1990 something. So without error, because error bag propagation, we can use it to propagate error backward and adjust weights. So 1940, 1945, they discovered a perceptron. So they used this perceptron. Yes, how to decide the value of bias? Yes, yeah, this is a problem. How can we decide it? What do you think? Yeah, Hisham? How can we decide the bias, please? Can anyone answer? How can we decide omega 1 and omega 2? Okay, I need to escape. Yes. Yes, I will add one more slide here because yes, can you try, please? How can we decide omega 1 and omega 2? As I told you, Hisham, we have this problem. I mean, if our problem is in two-dimensional space, if I can draw it in two-dimensional space, and I have one class here, which is those circles, and I have also I have another class here which is squares, and I need to classify it. So can you propose a line for classifying it? My model should generate a line. I need a decision line. So in fact, my decision line will be this one in the middle, right? This line is very good line. And all data points which are located above the line, it will be classified into +1, for example. And all data points below the line, it will be classified into -1. And after training your model, you will get a new point, correct? Maybe in testing or after implementing your model. So I will train my model. My model will be able to generate this nice line. And after that, I need to test it in the hospital, for example. I need to diagnose patient. I got a patient, and I need to see if this patient has cold or has a certain disease or not. So I will get the input features, and I will feed my input features to my model. Imagine it's two features. So I got a new example here, which is this triangle. So I have those points are xy. In fact, this is x1 value and the x2 value. I will substitute those two values into my decision line, and those 2 points I will get a value. If this value is above the line, positive, it will be classified into +1. If it is negative, it means this triangle is below the line. It will be classified into 0. So how can we characterize this line? We characterize this line with omega 1, omega 2, and the biased values. Those are my model parameters. Because this line has an equation. This equation will be omega 1 x1 plus omega 2 x2 plus b equals 0. So all points which are located on the line, it will generate 0, right? And all data points above the line, it will generate +1. All data points below the line, it will generate a negative value. So the output from this equation, we will send it to my activation function. And my activation function, it will classify it into a number, +1, -1, or +1 and 0. So we will go to the question again, Hisham. How can we select omega 1 and omega 2? If you change it omega 1 and omega 2, you will change the slope of the line. So the line, the slope will change. If you increase omega 1, decrease omega 2, the slope of the line will change. How can we select B? In the data set in front of you, if you select B equals 0, the line will go through the origin. And if this line goes through the origin, I'm sure that the accuracy here will not be more than 50% or 50, maybe 51%, 52%, because all data points, those data points will be correctly classified. All those squares above the line, it will misclassify. Maybe except the point below the line, it would be, so maybe the accuracy would be a little bit higher than 50% if you selected B equal 0. So it's not smart in this problem to select B equal 0, right? Because I need to shift my line up. So in this case, you need to change the value of B. You can select B positive or negative to shift the line up and down across x2 or y-axis, because this is a y-intercept or x2 intercept. So I need to intercept here in this point, not in this point. So in this case, I need to select B. So how can we do this? We will consider B as a weight, and we will adjust, we will let my perceptron learning rule to adjust it. We don't need to do it manually, for example. I will just consider B as a model parameter, and I need my optimizer to adjust it, to select it for me. We don't need to care about this. Yes. Do you have any question, Hisham?
Yes. Actually, currently you just draw a linear line and there are two classes. If
Yes.
two clusters basically.
Yes.
Above the line cluster represent positive class and below that represent negative. This is as far as I'm concerned, this is in case of if data set is actually balanced. Suppose we have imbalance or chaotic data set, then this linear line will not work. So
Yeah.
instead of manually starting from instead of giving a manual value
Mm-hmm.
of bias, we should prefer techniques like because we are talking about multi-layer perceptrons,
Mm-hmm.
we should target like learning through training or empirical testing or maybe automated optimization like Bayesian optimization
Yes.
or random search instead of
Yes. Yes. I agree
manually.
with you.
Yeah.
Yes, I agree with you. We will do it automatically. As I told you, we are not able to do it by trial and error, unless your data set is very simple and it's in two-dimensional space. But if your data has a higher dimensionality, for example, it will be difficult to visualize, and it's difficult to work with manual approach. We need to automate it. So we need to use an optimizer, and this optimizer will be able to adjust it for us. And in fact, how this optimizer works, um, um, how the optimizer will work. Can you imagine how it works? Yes. Okay. So how this optimizer will work? Can you imagine? So usually the optimizer, I have my data sets here. I have my data set. So this is my data sets, for example, circles and the squares, for example. In fact, the optimizer, as you know, in artificial neural network, we initialize the weights with some random values, small values, or zero values. Imagine that you are you are initializing the model with zero values. So omega 1 equals 0, omega 2 equals 0, and the b equals 0. So in this case, in fact, the slope of the line will be 0. So maybe the line, we will start with a line parallel to x-axis. We will start with a line like this one. And after that, incrementally, we will change weights step by step. So maybe the line will start moving little bit by little bit. It will go up little bit by little bit until we have a line which has an accuracy of 100%. In this case, we will stop. So the algorithm, in fact, which we will use, we need to initialize the weights to very small random values or to zero values, for example. And after that, in number of iterations, we will adjust the value of omega 1 and omega 2 and the bias. So step by step, this line will start moving until it is capable of classifying the data correctly. So you can say that, okay, I will train my model for 10 iterations. So after 10 iterations, it will stop, and we will check the accuracy of the model. Or you can just say that I will keep the model training until we achieve accuracy of maybe 95%, and we will stop. So the training process will start by initializing the weights and the bias to very small random values. And after that, in each iteration, we will try to make small changes to the weights and the bias. And maybe after 10 iterations or 20 iterations, we will stop and we will check the model accuracy. So now we need to implement our model in Python, for example. So how can we do this? How can we implement a perceptron? The perceptron, it's a very simple equation as we agreed on, right? So we have two inputs. Just do it for two inputs. You have two inputs, x1 and x2. x1 and x2 is connected with my perceptron using weight value omega 1 and omega 2. We will calculate the weighted sum here. So we will get a value called the net. So this net value, it will be omega x plus b. Just add b here, right? So this one plus 1 multiplied by B, right? With a bias, B or bias, for example. So calculate net. How can we calculate net? Net, it's just omega x plus B, right? And I used here dot product because I will define the weights as a vector. So this weights omega, it will be just a vector of omega 1 and omega 2. X will be defined also as a vector because I have two inputs, x1 and x2. And B, it's a scalar, right? So we need to calculate this net. So net equal omega transpose x plus B. You can use dot product to implement it. And just remember to add bias because we need to have bias. Without bias, we assume the bias equals 0. So if you didn't use bias, for sure your decision line will go through the origin. And when you go through the origin, you will limit yourself. Maybe you will not be able to achieve good accuracy. So and after that, I need to apply this net value to my activation function. This one, we call it activation function or threshold or something. So just apply this net value. So if this net value is higher than 0, right? If it is something here, it will be classified into +1. Otherwise, it will be classified into 0. So in this case, we can get the output to be +1 or 0 based on x1 and x2. So now we need to do it, and we need to test it with a data set, right? We need to test it with a data set with AND gate, for example. So I have it here. I just want to share the link with you so you can. I don't know where is the link. Okay, maybe this perceptron with a logic. So I will get this link to you, and I will. Okay, just 1 second, please. I will share this link with you so you can. I will share this link in the chat, please, so you can just open it and try to play with it. You have it in the chat. I will open it as well in my computer here. Okay, I will share. Can you see my I don't know. Can you see my screen? Yes. Can you see my screen, please? Yes. Okay. So now we need to implement this. Perceptron, right? And we will do it just manually, right? You just need to select values for omega 1 and omega 2. So here, as you can see here, for AND, for example, I selected omega 1 equal omega 2 equal 1, and the bias equal -3 divided by 2. And for the OR gate, it will be omega 1 equal omega 2 equal 1, and the bias will be -half. And after that, I will import. I have a problem here, in fact. Maybe I need to open it in Google Colab. Yes. So it will be like this one. So as you can see here, this is my first perceptron. You just need to define a function, this perceptron, and it has inputs, weights, and bias. And you need to use it for prediction. So we need to get predictions. And I will just use this for loop and go through the inputs and try to calculate prediction. So first I need to calculate net value. So net value, it will be omega multiplied by x, omega transpose x plus bias. You can just use here dot product. And after doing this, you can use a function called the sign function. This sign function, if you will test the net value, if the net value is positive, you will get 1. Otherwise, you will get 0. So you can just use a sign function, or you can just implement this. If net greater than or equal 0, y equal plus, otherwise y equals 0. And append the prediction into a vector called predict and just test it. So so this is my function. And I will test it with those numbers. So I will try here to test it with for AND gate. I'm selecting those omega 1 equal omega 2 equal 1 and the bias equal -3 divided by 2. This is my test data, my data set. It's 0, 1, 0, 1, 0, 0, 1, 1, all possible combinations of inputs. And the target value will be 0, 0, 0, 1. So and I will plot it. So you will get this one. So this is my AND data set, right? So this is it's AND. So this yellow one, it should be 1 and 1. 1 and 1, it will be classified as +1. And the other three values will be classified as 0, right? And then when you select those values, try to select this one 0.5 to see what will happen. So I will just change this one into 0.5, for example. Sorry, should be dot. So try to see. So we got different line. So when we change omega 1 and omega 2, okay, I will select B equal 0. I will just put this one equal 0. And I will put this one again into 1. Just make it one more time. And I will test my model. Do you see what happened? So the line still has the same slope, but now it goes through the origin because I selected B equal 0. So when you change the B value, the line will go through the origin. Can we select it negative value? Yes, I can. Maybe positive value, so it will go up. So it will be, for example, 0.5. So now it will go, it will go down. When it is positive, it will go, now y-intercept, it will intersect y-axis at minus 0.5, right? Minus 0.5. So when you change this bias value, the line will shift, go up and down in your, search space or in y-axis, across y-axis, for example. But when you change omega 1 and omega 2, it will change the slope. So let us change this one into -1. So you will get a different line. Do you see the line now has positive slope, correct? So omega 1 and omega 2, it will control the slope of your line, and the bias value, this is the y-intercept. If you set bias equal 0, this line must go through the origin. Now it's 0, so it will go through the origin. So it will be difficult to classify your data sets. Now what is the accuracy? Calculate the accuracy. So the accuracy will be different. So the idea here, your model is very simple. Your model has two inputs, x1 and x2, and you have two weights, omega 1 and omega 2. So it's smart to increase your degree of freedom. Your degree of freedom, you can increase it by adding the bias. So you need to change omega 1 and omega 2. When you change omega 1 and omega 2, you will change the slope. And when you change the slope, you will be able to find a good line, which will give you better accuracy. So your model can successfully classify your data. And the bias also is very important. So this is just an example for AND. This is plotting it in different way, for example, the decision line. So here, when we are plotting it, I need to go to the slides because it will be much easier. But here, I generate all possible values for x1 from minus 0.1 to 1.5 using this step. So I will generate some values for x1 because I need to draw a line. And for x2, I will get x2 from the equation. The equation was net equal omega 1 x1 plus omega 2 x2 plus p equals 0. So if you have x1 value, you can get x2 values. So x2 will be minus omega. It will be minus omega 1 divided by omega 2 multiplied by x1 minus bias divided by omega 2. So just find values for x2. And after that, you can just plot x1 against x2 to plot your decision line. So we will do it in the slides. This is another way for plotting your decision line. It's just using a mesh grid. Mesh grid, it's a nice way. So I will generate all possible values for x1, all possible values for x2. I will use a mesh grid to get x grid and y grid. And after that, my perceptron, I will send it to my perceptron xg and yg. And in this case, I will get the classification in three-dimensional space. I will get zg, and I will use a scatter plot, which will plot xg against yg, and the classes here equal zg. So I will get positive values and the negative values from this function. All positive values will be classified into yellow, and all negative values will be classified into blue, and so on. So we can plot it in a much nice way. This one for the OR gate. So it's the same model, just changing x1 and x2, choose different values for omega 1 and omega 2 and the bias. You will get a good decision line. So it will be like this one. For XOR, it's complex. No, XOR, it's complex problem because we cannot solve it using a perceptron. We need to solve it using MLP. And because we didn't study error backpropagation. So I will just select values by trial and error, right? Based on my experience, for example. So I will define like a feed-forward neural network or multi-layer perceptron. So it will consist of, it's very simple. I will have a hidden layer, and the input to this hidden layer will be X, and the weights will be omega 1. But here, omega 1, in fact, it will be a matrix, not a vector, right? So when we need to define here omega 1 should be a matrix, because I have 2 units. I will explain it also in the slides one more time, but omega 1 will be a matrix 2 times 2. And the bias here, it will be an array. It will not be a scalar value, but it will be array because I have 2 units. So each unit will have a bias value. So it should be a vector, 1 times 2, as you can see here. Those are the values, in fact, which I used from OR and AND. And after that, we will have, so I will get H, which will be the output from this hidden layer. So H will be this hard limb omega X plus B, right? Once you have H, H will be the input to the output layer, right? So I need to multiply H by omega 2 and add another bias, which is B2. And you will get your classified value. So the output here will be this hard limb of the dot product of omega 2 multiplied by H plus B2, for example. I will test it with my data. This is the data set of my XOR. So the input will be 0, 1, 0, 1, 0, 0, 1, 1, or possible combinations. And the labels will be 0, 1, 1, 0. And yes. So I called it feed-forward neural network, in fact. So I call it FNN. So after defining it, I will just provide X to my model, and Y will be my prediction, right? So we will do it. So you will get this decision lines. So all data points which are between the 2 lines will be classified into +1. All data points above and below, it will be classified into 0. So now we can solve more complex problems, in fact. And this is a line, in fact. If you want to make it curve or little bit nonlinear, we need to use different activation function, or we can make some tricks. So you have the code. I will just let me know if you want to take a break, right? If you want to take a break, just let me know, please.
How long do you have you scheduled for today, Ibrahim?
We will work until 12 or 12:30.
Yeah.
Yeah. So do you want to have a break, or should we just continue? Should take 5 minutes to get coffee, or?
I'm fine for me, but maybe anyone else has an opinion.
So other people, please, do you want to get a break, or should we continue?
I'm fine too.
Okay, so we can just continue. Yes. Okay, so now we have this perceptron. So please try now to implement, just open a file, maybe in your computer, Jupyter Notebook, or in Google Colab, just a new one, and try to implement this perceptron. Yeah, we need to implement a perceptron. So just the perceptron is very simple. We need to have this decision line. This decision line will be net equal omega X plus B. So try to implement it. I mean, forget about the link which I shared with you. Try to do it by yourself. We need to implement a perceptron, and we need to test it with an example like AND or XOR, or sorry, AND or OR dataset, for example, or iris dataset. In fact, we can use it with iris, right? So now first try to implement your first perceptron. Just remember, the function is very simple. We need to get a decision line. This decision line will be net equal omega X plus B equals 0. This is my decision line. And after that, we need to classify my data set. All points which are located above the line, it should be classified into +1. All data points which are below the line, it should be classified into -1. So try to write a very simple code for your first perceptron. Forget about the one in front of you. Maybe you will do it in a much better way. So we need to get net. So net will be this, dot product, omega transpose X plus B. And after that, I need to apply this net to an activation function, right? You can use sine function or you can use this one. Maybe you can just use y equal sine function of net. So in this case, it will be converted into +1 and the -1. 0, sorry. If you want to use symmetric activation function, so it's called hard limb, or yeah. So just it changes this one into -1, right? And select if you will test it with AND. So this is AND data set 0, 1, 0, 1, 0, 0, 1, 1. And the output will be, when it is AND, it will be 0, 1, 1, 0. If you want to test it with OR, sorry, this is OR. And when it is AND, it will be like this one. It will be 0, 0, 0, 1. Yes. So just try to do it, please. And try to plot the decision line. So try to implement, forget about the code which I shared with you. Maybe I shouldn't do it early. So we can do it step by step. So as a guideline, I mean, this simple code which I'm sharing on the screen, you can use it as a guideline for helping you, but try to write your code step by step. We have two inputs, so the decision line will be like this one. So for this AND gate, for example, so it will be ω1 x1 plus ω2 x2 plus p equals 0. If you have values for x1, so we will get this linear space. We can get some values for x1, and I need to get x2. So x2 from this equation, it will be just take ω1 x1 to the other side and b to the other side. So it will be negative ω1 x1 plus b divided by, we need to get x2, so divided by ω2. So it will be like this one. So if you want to draw the decision line, you need to assume values for x1 using linear space. And when you have values for x1, you substitute it into this equation to get x2. And after that, just plot x1 and x2, you will get this decision line. You will be able to draw the line. So this is one approach for plotting the decision line. This one we call it decision line. Yeah, because in fact, I can get the accuracy like, okay, the accuracy is 100%, but it would be beautiful if we can draw the decision line to see how the model will perform. All data points above the line, it will be classified into +1. All data points which are below the line, on or below the line, it will be classified into 0, right? We have this command in Python. It's called the linear space. This one, this function, you can use it for getting values for x1. So you can say that, okay, I want to generate all data points between, for example, between 0 and 1 using this step, right? Or you can use this function for generating all data points between 0 and 1 using this small step, using this function called arrange or linear space. In this case, it means here I need to generate 25 values between 0 and 1. So this is your grid size or cell size. So here I use this linear space to get values for x1 and x2. And after that, I will send the x1 and the x2 to this mesh grid function. It will generate x grid, y grid. And I will substitute those values to my perceptron, because now I trained my perceptron now to classify. So I will send all those points to my perceptron, and it will classify if each single point onto +1 and the 0. And after that, I will plot it using a scatter plot using this function. So I will have this. So this is in fact my decision line. And this one means all data points in blue are +1, classified into +1, and all data points in magenta, I guess, it will be classified into 0. So it will be much easier. I mean, this approach using this mesh grid is much easier when your model is complex. So when we are working with MLP, for example, multi-layer perceptron, we cannot find this equation. It's impossible to find this decision line equation because it does not exist. It's too complex. So it's much better to use this approach for plotting your decision boundary. Decision. So I can give you 5 minutes to work on the Python and implement your first perceptron and play with numbers omega 1, omega 2 bias. Select the different numbers and plot your decision line. And you will share your screen with me, please. And we need someone to share his screen with me so he can show us that we can get different lines for different weights and the bias. So we can take 5 minutes or 4 minutes. We can start at 10:20. People can share screen and they can try to show us, their model. Hello, everyone. Is there anyone who can share his screen? And I need to stop sharing. Is there anyone who would like to share his screen?
Not entirely done, but
Okay, so you can 1 more minute.
yeah.
Okay. Yes, Hisham, can you share your screen? Anyone who would like to share his screen and just I cannot hear anyone. Axel, maybe I guess you are talking, but you are muted.
Yeah, still not done in that sense. But I'm not try to figure out how to do the
Decision
plotting
line?
as you did. Yeah, I can just share it. I can be the donkey in that sense.
So is the most important?
I'm not able to share it.
Okay.
To share the screen.
You cannot?
No.
Can you try one more time?
Disabled part. Yeah.
You should be able to share, correct?
Now I am.
Okay. So we have the perceptron defined. So y
yeah, that's
equals,
just a simple.
Okay. So it's omega x. We need to calculate omega x. Omega Why it's multiplied? So it's okay. We will get the same. No,
Is it
this
the
one
same?
will, because it's according to the definition. It should be, we need to stick to the definition omega x, omega transpose multiplied by x, right? It's omega transpose multiplied by x, not at. In fact, it's asterisk omega transpose dot x multiplied by x. Mhm. And you have inputs x.
Yeah, just
Oh,
these, for example.
Yes, x1, x2. You want to use mesh grid.
Yeah, that's what I didn't figure out.
Mhm.
So I'll try to figure out these.
You have some error here.
Yeah, it's probably haven't been.
Okay.
Yeah.
So anyway, thank you. You can complete it after, after the lecture, for example. But it's a good exercise to just to practice. Yes. So in fact, it will be nice if yes. So we did that for also OR gate. So OR gate, it will be the same. We just need to change the data set. The data set will be the same, but the target value will be it will be just for OR. It will be 0, 1, 1, 1, and just I want to explain this equation for you. So this one, it's my decision line. This is my decision line. So you just need to find values for x1. Once you have values for x1, you can substitute it into the decision line to get x2. The decision line, it's omega 1, x1 plus omega 2, x2 plus p equals 0. So if you can assume values for x1, we need to get x2. So x2 in this case, it will be minus 1 divided by omega 2 multiplied by omega 1 x1 plus p. So now we can get x2. Once you have x1 and x2, you can just plot it to draw the decision line. So this is one way for doing it. And when you look into this decision line, any point which are located on the line, it will generate 0. So if we can say that net value will be 0, so we can say that net equal, what is omega 1 here? In fact, we can select the values. We select omega 1 equal omega 2 equal 1, and the bias, it was minus 3 divided by 2. Yes. Where is the bias value? Bias value equal minus 3 divided by 2. So minus 3 divided by 2. So the line here, in fact, it will be x1 plus omega x plus x2 minus 3 divided by t. Just select any point to test it. Select this point. This point, it's 1 and 1. So in fact, this point, it would be, if I substitute this value into the equation, so this one, it will be 1 plus 1 minus 3 divided by 2. So it will be 0.5. 0.5, it's positive. So when we send this 0.5 to my activation function, which is this activation function, so it's 0.5, right? 0.5. So it will be classified into plus. Let us select another point. This point, for example. It's or, not and, in fact. It's or. When it is or, it's negative, it's minus 0. So sorry, this one, it's minus 1 divided by 2. So it will be 1.5. So 1.5, it's the positive. So select another point like this point. So the coordinates of this point, it's 1 and 0. Substitute this value into this net function. So it will be 1 plus 0 minus half. So it will be 0.5 positive. So also this one will be classified into plus 1. So this one into plus 1, this one into plus 1. This point also, it's 0 and 1. This point, it's 0 and 1. Substitute this value in this function net. So it will be 0 plus 1 minus 1 divided by 2, so it will be 0.5. So it's still positive. Select this point, which is below the line. This one, it's 0 and 0. Substitute this value in this net, so it will be 0 plus 0 minus 0.5. So it will be minus 0.5, which is negative, less than 0. So it will be classified into minus 0.5, so it will be classified into 0. So this is how those classification problems are working. So as you can see here, we are getting numbers, negative, positive, and after that we will convert those negative values and the positive value into a label. This label, it will be +1 and a 0, for example, or +1 and a -1. So in fact, when we are solving the complex problems, because my neural network know nothing about text, it cannot classify into dog and the cat. I need to replace dog and the cat with a number, numerical value. This numerical value, it could be +1 and the -1, or +1 and a 0. It's according to the activation function or the threshold function, which we will use here. Yes, so the problem for XOR, we discussed it before, that one perceptron, it's difficult to classify it using a single line. We need to have 2 lines. So I need to generate 2 lines. So we will say that, okay, all those black squares, all data points which are between the 2 lines will be classified into +1. Data points above, it will be classified into 0. Points below, it will be classified into 0. So in this case, we can classify XOR, because XOR dataset, it's like this one: 0, 1, 0, 1, 0, 0, 1, 1, and our labels or target values will be 0, 1, 1, 0. So as you can see here, this point which is 1 and 0, it's 1. This point which is 0 and 1, it's 1. And this point is 0, this point is 0. So we need to find, I mean, it's complex. I cannot solve this problem using a single line, because with a single line, maybe maximum you can achieve accuracy of 75%. So it's not closer to, it's not 90%. We will not accept this accuracy. We need to build a model with a better accuracy. So to solve this problem, we need to build a multi-layer perceptron. We call it MLP, or feed-forward neural network. I mean, some people, they call it feed-forward neural network, or MLP, multi-layer perceptron. Both are the same, right? So the most simple case here is to generate 2 linear lines. So this line will be generated with a perceptron. This line will be generated with a perceptron. And after that, I need to combine the decision into, because this line will generate 0, 1, this one will generate 1, 0 something. So it will be confusing for us to use only 2 perceptrons. So we need to combine the decision into 1. So we will use 1 perceptron for generating this line, another perceptron for generating this line, and at the end, I will use an output layer. This output layer, it will try to combine the decision from those 2 lines. So in this case, we will have a multi-layer perceptron. So if I want to plot it, it will be like this one. So I will have 1 perceptron. Oh, sorry. I will have one, sorry again. Yes. I will have 1 perceptron, and I will have another perceptron. I have my problem here. It has 2 inputs, one called X1, one called X2. So I will feed those to my inputs, right? And after that, I need to use another, why I cannot select 2 different lines, colors. So I need to have another one which will combine the decision from those 2 perceptrons. So in fact, this one, it will generate 1 line. This one will generate 1 line. This one will generate another line, correct? And this output layer, it will combine the decision to get only single decision. Because if you have an input X1 and X2, I need to get decision. Is it 0 or 1 directly? I don't need to get more confusing numbers. So if you have here 0 and 0, I need to get here the output to be just 0, right? But if you will use the first line, this line will make some decision, because this 0 and 0, it's this point, it's here, in fact. So it's below this line and it's below this line, correct? So this line will say, okay, this is this one, it's 0 because it's below the line. And with respect to this line also, we will get a 0, right? So I need to combine 0 and 0 into 1 single. Is it 0 or is it 1, for example? So now I need to combine those decisions into 1 decision, and I want to say now this point is 0. If the point is below the line, what will happen here? So for this line, it's +1, and for the other line, it's 0, in fact. So we will get a decision like 0 and +1. So I need to combine 0 and +1 into +1, for example. So in this case, we will build a multi-layer perceptron. So this multi-layer perceptron, it's very simple. it consists of one input layer, and one hidden layer, and an output layer. And if you can find those numbers, weights and bias, without using error backpropagation, it's okay. Now we are happy because we can just solve it. But of course, for complex problems, it's impossible to solve it by trial and error or by visualizing it, because it's time consuming. So it's very important to use error backpropagation to adjust the weights of this model. In the training process, we will initialize weights. I mean, we have here omega and V weights. So omega here, it will be omega 1, 1, omega 1, 2, omega 2, 1, omega 2, 2. It will be like this one. So the weights of the input layer. The weights of the hidden layer, it will be like this one, V1 and V2. Right? And we have bias. Maybe B1, it's equal B1, B2. And the bias B3. We have also B3, which is just B3 for the output layer. So if I want to write this equation, if I want to code it, it's easy. So it will be like, I need to get net 1, the output from the hidden layer. So H equal sine function of omega X plus P. So now I will get the output. So this one output will be H1 and H2, for example. So I will get this one. And after doing this, so H will be the output from the hidden layer. Now we need to get the output from the output layer. I will call it Y. So Y will be sine function. We will agree that we will use the sine function. So it will be H multiplied by V, or V multiplied by H plus B3. Now we will get Y. So it's 2 lines. So now it's straightforward neural network, but in fact, its implementation is very simple, right? Using this matrix multiplication, it makes life much easier. I remember the first neural network which I built, I was undergraduate at that time. I used for loops because, I mean, it was difficult for me to understand matrix multiplication. So if you want to avoid this matrix multiplication, you need to write a for loop, and it will be very complex. But now in Python, we use matrix multiplication. You just need to multiply omega by X and add to it B, right? B is a vector. Omega is 2 times 2. This one, it's 2 times 1, in fact. So when you do this multiplication, it will be 2 times 1. So this one will give you a vector like this one. B also is 2 times 1. So you will get 2 times 1. So H will be 2 times 1. So it will be H1 and H2. Multiply H1 and H2 with a V, which is V1 and V2, and add to it B3, and that is it, right? And we're using the sine function here. The sine function, it's a step function. So sine function, it will be like this one, right? This is my sine function. If it is positive, it will give you +1, otherwise it will be 0. So sine function will be my threshold function or my activation function. So my model will look like this one, and this was the weights which we got. So in fact, the first one, it's AND, the second one, it's OR, and we just try to subtract. Do you see? I multiplied the output from OR by +1 and the other one by -1. So I just try to subtract OR from AND, right? If you want to get this XOR, it will be like OR minus AND, right? Yes, if you can look into the truth table here. So this is OR, this is AND, this is XOR. Do you see? If you subtract this one from this one, so 0 minus 0, it will be 0. 1 minus 0, it will be 1. 1 minus 0, it will be 1. 1 minus 1, it will be 0. So in reality, it's OR minus AND, right? And that is why I selected this one positive, this one negative, right? So it's weighted sum, but it will make something like subtracting OR from AND, or subtracting AND from OR, right? And you will, of course, you need to select this good numbers, otherwise you will get wrong decision. So this one, it's multi-layer perceptron. This multi-layer perceptron consists of input layer. This one, it's hidden layer. And we have here output layer. Just using perceptron. I mean, we didn't study error backpropagation yet, but it's easy to do this. Of course, if you want to make it more complex, so for example, this model, in fact, it will generate decision line, which is a straight line. When you look at the decision boundaries, it will be just line and line. If you want to make something fancy, more complex, just add one more perceptron here, right? So it will be 3 perceptrons. So now it will be more complex. You see, it will be like this one. So now it's more complex. And now I cannot train it by myself, and I need to use maybe error backpropagation to adjust it. So try, in this case, in fact, instead of having straight lines, maybe it will be something like this one. It will be something fancy, right? You will get the session boundary, which is more complex. Yes. So now we need to implement this XOR. I will call it hard lim. I don't know why, but it's hard lim because we are using this hard lim or step function. So I defined a function called hard lim, but you can use sign function. In fact, you don't need to use this one. So I defined a function called hard lim because this step function, in fact, in any machine learning book, they call it hard lim function, hard lim. So or you can just use sign function. And this is my feed-forward neural network. In fact, I prefer to call it MLP because feed-forward neural network, there is no mention to perceptron, and it's bad. If I'm a perceptron, I will not be happy. So I like to call it MLP because it's multi-layer perceptron. So we did that before. We have 2 layers. So this one will be the output from the hidden layer. This one, it's the hidden layer. And in fact, this output, this one, it's the output from the output layer. And you know that the input layer, it does not make any sense. I mean, input layer, it's just to transfer inputs to the first hidden layer. If you want to add one more hidden layer, just add it here, please. So if you want to add one more hidden layer here, so I will call this one H1, and I will add another one here. I will add another equation, for example, H2 equal, I will write it here because I cannot write here. So it will be H2 equal hard lim, this dot product of, I will call, for example, omega 2 multiplied by H1, comma B2, for example. It will be like this one, and call this one B3. So if you want to add more hidden layers, you can do it by just adding one line. So the implementation is extremely simple. So one layer in your feed-forward neural network or multi-layer perceptron, it can be implemented just using one line of code. This one line of code will be the dot product of weights and input, right? And of course, this applies the activation function, which is hard lim here. We use the step function here as, so it's just a dot product of omega 1 x plus b, and apply it to the hard lim function to get classification. So in fact, H1 now will be something, it will be 1 and 0, and Y also it will be 1 and 0. So easy, right? If you want to change the activation function, because here I'm using this step function. If you want to use sigmoid, it's okay, because sigmoid, it's nonlinear. So if really your problem is more complex, because this function is very, very simple, right? This step function is very simple. But if you want to add more complex activation function like sigmoid, you can just add a sigmoid, no problem, right? So now we need to test it. So I need to build I need to define first omega 1 and B. So omega 1, it will be matrix 2 by 2. It will be matrix, not vector. When we are working with a perceptron, it was a vector. But when it is a multi-layer perceptron, it's a matrix. So this one, in fact, it's like this one, right? And the B1, we have B1, we have omega 2, B2. Just this is my data set. Inputs are the same. Just the target value will be different. It will be 0, 1, 1, 0. Just feed the input to your network and get Y. And after getting Y, you need to calculate. In fact, you need to calculate accuracy. So accuracy will be Y minus T, the absolute value, right? Or just count values where Y does not equal to T, right? So anyway, those are the targets, and those are predictions. So we can predict it by 100% with 100% accuracy because we selected good numbers. But selecting those numbers is complex, right? Selecting those numbers, it's complex, and it's much better to try to use an optimizer to optimize it, to find good combinations. Because if you are working with a large data set or a complex problems, it's impossible to find those numbers by hand. It will be very time consuming. So it's much better to try to use an optimizer like error backpropagation, which will try to adjust those weights. We call it learning. So in the learning process, we initialize those weights with small random values, right? And after that, start calculating, going forward to calculate Y. And from this Y, we calculate error. Y minus T, error will be Y minus T, right? Y minus T is error. So we need to define a loss function. It could be the error, for example, Y minus T, and we will try to minimize Y minus T, right? So the optimizer will try to adjust weights in a way which will minimize this error function or loss function. Yes. So if you want to draw it, if you want to plot your decision boundary, for example, so you just need, as I told you, you need to define values for x1 using linear space, values for x2, use mesh grid to generate xg and yg, and after that you will feed your model, your feed-forward neural network with all those xg value and yg value, and you get each point classified. So in fact, what we are doing here is it's like this. My data set, it's across x1 and x2. I will create a grid, right? I will create a grid and another grid here, like this one. So I will get those values, right? I will get those xg and yg values, and I will send all those values to my model to classify it, right? And I know my model is like two lines here. So in fact, all points which are below the line, it will be classified into zeros. All points which are above the second line, it will be classified into 0. And all points which are between the two lines, it will be classified into +1. And we will plot it. So you will get those numbers in ZG. And after that, you use a scatter plot for plotting it. So it will be very, very easy. Yeah. So now we understand perceptron, and we can adjust those weights by hand, by trial and error. Now we need to learn an approach to automatically adjust it. Feed-forward neural network, we can use error backpropagation. But for a perceptron, there is something simple rule called perceptron learning rule. This perceptron learning rule, it will help us to adjust the weights automatically by working with the data set. So we don't need to we need to select it manually. We can just build our model and try to train our model to find a good combination of omega 1, omega 2, omega 3, and the bias, for example. So this perceptron learning group, it's very simple. We need to start by initializing the weights to 0 or small random values. Why do we need to do this? Why do we need to initialize weights and the bias? Because without initialization, we cannot do multiplication, because I need to do multiplication. I need to calculate y, and y equal omega x plus b. So therefore, I need to choose values for omega and b, some small values or 0, for example. And after that, for each input, we need to calculate the output value. So I have my model here like this one. So this is b, this is omega 1, omega 2, this is x1, x2, and this is my model, right? This is my model. So I will apply the first input, x1 and x2, and I will calculate y1, right? So this is my data here. I have here x1, x2. So I will go to the first example, and I will apply those values, and I will see t1. I will calculate y1, and I have the value, the label for this example, which is t1. We will calculate the error. So the error here will be, the target value minus output. So it will be t1 minus y1. It will be the error value. Once you calculated the value, you will adjust the weight. You update the weight using this simple rule. We need to calculate something called the delta omega, rate of change, or small increment, small change in omega. It will be coefficient called eta multiplied by the error multiplied by the input. So it will be eta multiplied by error. T minus y, this is the error, multiplied by the input for that example. We just need to adjust update the weights using this value. So we'll calculate delta omega. Once you have delta omega, you can just update omega. So omega equal old omega plus delta omega. And you did that for weights. You do the same for bias, right? And remember, the bias, it's this b value. And we assume that the input to this bias, it's a +1. So we need to calculate delta b. So delta b will be eta multiplied by the error multiplied by 1. Because for this bias, we don't have input. In fact, it's +1. The bias, it's the weight for this input, and this input, it's +1. Right? So, and we will repeat this process several iterations until the weights are adjusted. So let us take an example. Let's assume that the output for this example should be 1, for example. We assume that this output should be 1. And we initialize the weights to 0 value, or we assume that, I mean, any value, any weights are small value, or x1 and x2 are zeros, for example. Imagine x1 and x2 are zeros, right? We initialize the weights to small random value, multiply omega by x. So we will calculate net, which is omega x plus p. So b is small, 0, and omega and the x are zeros. So this value, in fact, it will be 0, right? Apply this 0 to our activation function. So the output will be 0. So when the net is 0, y will be 0. So in this case, we will calculate the error. The target for this example, it's 1, and the prediction is 0. So we will calculate the error, which is t minus 1. So the error will be 1 minus 0 equal 1, right? So in this case, what will happen? We need to update the weights. To update the weights, it will be constant small coefficient. We call it learning rate. It will be multiplied by the error, which is 1, multiplied by x. It will be multiplied by the input, which is x. And we will repeat this. We will do the same also with the bias. So in case of the bias, it will be eta, learning rate, multiplied by the error, which is 1 here, multiplied by 1. So delta B will be a value, and we will adjust B. So B was 0. So all the B was 0 plus delta B now, it's if this one is 0.5. So in fact, this one will be 0.5 times 1 times 1, so it will be 0.5. So new B now, it's 0.5. So now we are moving the line up and down, correct? Because we are changing the B value. We will repeat this process for several iterations until our line is in good location with respect to my data. So you are starting with some initial values. Maybe your line will start from here, and after that it will start moving, and it will adjust the slope. And at some point, we will get a line which has an accuracy of maybe 90% and 95%. And the accuracy cannot improve anymore. When the accuracy cannot improve anymore, we can stop training. So we have some termination criteria. The termination criteria is to train my model for number of iterations. You can say that I will train my model for 20 iterations. Maybe someone else, he will say that, okay, I will train my model until it cannot improve. So if I got my accuracy is 90%, the second accuracy is 95%, 95% now, there is no improvement for 3 iterations. So I can just stop the training process. You can make any conditions. We call it termination criteria. So this rule, in fact, is this perceptron learning rule. It's very simple. Delta omega equal learning rate or step size multiplied by error multiplied by input. Very, very simple. Learning rate multiplied by error multiplied by input. So all what you need to calculate the output. When you apply an example here, you need to calculate prediction. Subtract those prediction from target value to calculate error. And apply this equation. Calculate delta omega. It will be learning rate multiplied by error multiplied by input. Once you have delta omega, adjust to omega. So omega will be omega plus delta omega. And do this also for the bias. Because I got question from today that how can we adjust the bias? We will do the same for the bias. But remember, the input of the bias will be +1. So just multiply learning rate times the error. It will be delta B, and adjust your bias. We will repeat this process several times for number of iterations until we have good accuracy of our yes. Okay, so there are also some activation functions which we can use. For example, this one, it's a step function. We used it today. Some people, they call it sign function, right? Or hard limit, right? And we have this one also. Oh, sorry, this is sign function. Sorry, this is sign function. This is step function. And we can have also sigmoid. Sigmoid, it's nonlinear. I mean, this sigmoid, you can use it, but we need a threshold function because this one, in fact, it has some squashing effect. It will combine all inputs. It will convert inputs into a number between 0 and the +1, right? So you will get a number between, I mean, if it is classification problem, you will not get +1 and the -1 if you are using sigmoid, but you will get a number between 0 and 0.5. So it could be 0.6, which looks like probability. right? So if you are solving a classification problem using a step function, you will get only 0 or +1. Here in this example, you will get only 0 or +1. But if you will use a sigmoid, I will get all those numbers, right? I will get all those numbers from 0 to +1. So maybe I'm using it for classification problem, and I classify images into dogs and cats. If I will use a step function, I will get pure yes and no. I will get +1 and 0, for example, just this one or this one. But in case of sigmoid, you will get a number which is greater than or equal 0 and less than or equal +1. So maybe you will get 0.6. So what is the meaning of 0.6? It means the probability is that this image is for a cat is 60%. And the rest will be probability as a cat. It will be 40% cat, 60% dog. So in fact, in this case, you need to maybe use a threshold value to decide that this is a dog. You can say that, okay, all values above 0.5 would be classified as a dog. Otherwise, it will be a cat. So just remember, if you will use this sigmoid activation function, you will get a number, a float number. You will get a number between 0 and +1. So again, you need to follow it with something like this one, or you need to decide a threshold value 0.5. You can say that all probabilities higher than 0.5 will be classified into dog, and the rest will be cat. Or you can increase it. I don't know. Maybe in some places you need to increase this number to be 0.6, 0.7, right? Because maybe in this region or in this city, they have maybe large cats, right? If they have large cats, so if I will use 0.5 as a threshold value, maybe those large cats will be classified as a dog. So in this case, I want to adjust the threshold value. Okay, so now we need to implement our perceptron learning rule, and we need to use iris dataset. This is good practice. So I want you first, in fact, to load this iris dataset, plot it, and classify it using a perceptron. But I want to give you a hint. Iris dataset, in fact, load it from sklearn or Keras, for example. Iris dataset consists of 150 points. It has 4 features. So I will call it X1, X2, X3, X4. We have a target value here, right? So we have 4 feature values. We have here 4 columns, right? And in fact, the first 50 points, we have, it's like 3 blocks. It's like this one. The first 50 points are for Setosa. It's for a species called Setosa, right? Setosa. The second 50, it's for Virginica or versicolor, I guess. Versicolor. And the last 50 points are for species called Virginica. Right? So it's like this one. So it's a multi-class classification because here we have 3 classes. Right? We have here 3 classes. If you want to classify this one into 3 classes, you cannot use a perceptron because perceptron can use only for binary classification. Because we have only one output. I mean, from this perceptron, we have this one, this activation function or threshold, and we will get something like this one, +1 and 0, for example. That is all. If you have the output as +1 and 0, so chances to classify only for binary classification. I cannot have +1, 0, and a -1. It's impossible because I'm using this activation function, right? Even if you will use symmetric activation function, the output here will be +1 and a -1. So a perceptron can be used only for binary classification problem. So for this problem, you need to select the first 2 classes. Now I need to test the perceptron with this iris dataset. So we will select only the first 100 points because the first 100 points corresponds to 2 classes, Setosa and versicolor. And we will use a perceptron to solve this problem. So please, we will take maybe 5 minutes break, 10 minutes break. So you need to load this iris dataset, maybe from Keras or from sklearn because it is already there. Try to plot it. So plot T against X1 and X2 because we don't need to plot it in 3-dimensional space. Plot it in 2-dimensional space. So select select, for example, x1 and x2 and t. So plot x1 and x2, plot the two classes, the first two classes against x1 and x2, and see how it will look like. And please look into it and see, is it possible to use a perceptron to classify it? So can we use a perceptron to classify the first two classes of iris? I show you here because, but I will not share the code with you. I will let you work on the code. But this is Setosa and the versicolor, as you can see. And I'm plotting it against sepal length and sepal width, x1 and x2. So in fact, this one it's x1 and this one it's x2. And it's the first two classes. So it's Setosa in red and the versicolor in blue. We have two classes, and we are lucky because there is no overlap between the two classes, in fact. Can you see any overlap between the two classes? So there is no overlap. So in fact, x1 and x2 are very good for classifying those two classes. They carry lots of information to classify it. So in fact, we don't need to look into the other two features. So we will go back to point feature selection. Do you know what is feature selection? Feature selection, it's to try to select the most influential features which carry most of the information. If I can classify this problem using x1 and x2, we should not use x3 and x4 because it will be headache. Why should I x3 and x4? In fact, x3 and x4 does not carry any new information for us because x1 and x2 are enough. So to classify those first two classes, x1 and x2 will be very good, very enough. So please, the task now is to load iris dataset, plot it, generate this graph, and after that select a model, right? We need to draw a model using a perceptron. We will not implement the perceptron learning rule, but I will let you find the parameters of this model, right? I have this model. This is very good model. And this is y-intercept. It will intercept y-axis at some point here. Maybe it's 1.5. And as you can see here, the slope of the line is positive, right? The slope is positive. Maybe the slope is 1 plus 1. Correct? Because it's mixed angle of 45 degrees, for example. So you have the slope. You have the y-intercept. From the slope and y-intercept, try to find the value for omega 1, omega 2, and b. Because the equation of this line, in fact, it's omega 1, x1, plus omega 2, x2, plus b equals 0. So try to find a value for omega 1, try to find a value for omega 2, try to find a value for b, and draw this line, please. We will not use perceptron learning rule, but we will solve this manually by plotting it, by visualizing it. When we visualize it, we understand that we have two classes, and those two classes are not overlapping. So it's very easy, in fact, to just draw a line between the two classes to classify it. So we need to find the parameters of those of this line. This line will be generated by a perceptron. This perceptron will have two inputs, x1 and x2. This one connected by omega 1, omega 2. We have here bias, weighted sum, and after that we will use any activation function you like. If you want to use symmetric, it's okay. If you want to use a step, it's okay. So we will use here maybe step. Correct? It will be like this one. Plus 1, 0. So in this case, all points which are above the line, it will be classified into plus 1. All points which are below the line, it will be classified into 0. Right? So now you have everything. So start please by plotting. Plotting, we can take 10 minutes, 15 minutes, no problem. But the most important is to get hands-on. Yes. Anyone has any question, please?
I have a question.
Yes.
In the previous slides about the perceptron learning rule, for the bias, we multiplied with 1, but I just missed that part. Why did we do that? Can you explain?
Yes. Yeah, why it's multiplied by 1?
Yeah.
No, because we just need, in fact, they did that for one reason. I will explain it to you here in this white space. So we have a perceptron here. We have two inputs, for example, x1 and x2. We have here omega 1 and omega 2. We have here bias. So we will write bias here as a weight. And we will assume that this bias has plus one input, which is the same. And after that, we will apply our function. So this is one form. People, you can make it like this one. Other people also, in some old textbook, they make it like this one. So it will be like this one. The input here will be +1, and the weight here will be +1, right? So the weight will be +1, and the input will be the bias. Correct? Both, you will get the same results. In fact, both are the same. But I like this first one for one reason. In fact, if you want to simplify the equation of your perceptron, so instead of writing this is net value, so instead of writing net as omega transpose x plus b, you can write this equation as just omega transpose x and ignore b. We will add b into omega. In this case, omega will be defined as omega 1, omega 2, and the b, you will add it as a third row. And in this case, also x will be defined as x1, x2, and the +1. You see? So if you want to make your model more compact, so instead of writing the equation as omega x, omega transpose x plus b, you will just write, you will make it more compact. You will just write it omega transpose multiplied by x. But just remember to include the bias inside omega. If you want to include the bias inside omega, omega will be defined as omega 1, omega t, and the b. Right? In this case, we need to redefine x. So the input to my model, it will not be only x1 and x2, but it will be x1 and x2 and the +1. So in this case, in fact, when you use error backpropagation, this is very good, in terms of efficiency, because if you want to use error backpropagation, for example, to adjust, I don't need to write code for adjusting the weights and another line for adjusting the bias. I will just include b as a weight value with input equal +1. And then when we use error backpropagation for adjusting the weights, we will write it only one time. So we'll have only one line of code. So we will save some code from your program. You don't need to do it twice. One time for bias, one time for weight. Do it only one time for weights, but just include bias into your weight. Because, for example, here, if I need to adjust this one using perceptron learning rule, I need to calculate delta omega, which is eta multiplied by error multiplied by x, right? So in this case, I can do it for delta omega, and after that I can do it for delta b. But if you can include the bias into omega, you need to cancel this step. You don't need to do this step because it will be done here automatically, because omega now called omega 1, omega 2, and the b, right? So you calculate delta omega, which is delta omega 1, delta omega 2, delta b, so it will be automatically calculated in one step. So you just save some code, in fact. So when you define input as +1 to the bias in this structure, your code will be more efficient. It will be more compacted, right? You don't need to update bias again after updating the weights. You can just do it in one step.
Okay, thank you.
Yes, thanks. So now we will take maybe 10-15 minutes to try to first plot. First, you need to upload the data. Maybe you don't need to follow my way here, because here I used, in fact, CSV file. You don't need to do this. In fact, in reality, you don't need to do this, because you can download Iris dataset directly from sklearn or from Keras, right? You will get X and Y, and you need to split and so on, but you can get it directly from sklearn.datasets. sklearn.datasets. You can get Iris. So it will be much shorter. You don't need to do this. What I have been doing here, it's not the best way. So after that, because I downloaded it as a data frame here, and I did some, it will be automatically modified and adjusted for you when you download it from sklearn.datasets. So try work with sklearn or Keras, for example. And first, you need to visualize, plot. You need to get this graph, right? And after that, you need to draw a line. You need to select good values for omega 1, omega 2. You can select omega 1 equal omega 2 equal 1, for example. Maybe the bias will be some negative value, because I need to cut y-axis at a positive value. So maybe I can select bias equal minus 1.5, and plot the line and see how it will look like. So we will take 10 minutes break, and after that we will, during those 10 minutes, I can divide you into a break room if you would like to, so you can work together. Do you like? So do you like to work together in groups instead of working by yourself? You can use breakout rooms.
Sure.
Okay, we will
Okay.
try it.
Yeah, yeah.
So we will make, for example, how many rooms, how many people? We are 16. So we can just make maybe 2 people or 3 people working together, right? So we can make it 16 divided by 3. Okay, we'll make 5 rooms, right? It will be assigned in random. Yeah, so see you after 10 minutes. I guess I did a mistake, so sorry for this. Close all rooms. Yes, if just one from each group, he can just present his project quickly, please. Is it possible? Just one from each group, if possible. Hello, everybody.
Hi.
Yes, can be just one from each group, just to take 1 minute for presenting his answer.
I can show it. Okay, can you see my screen?
Okay, very good. Yes.
Yeah, like what we did was something on it again. So this is the chart that you were asking.
Yes.
So basically we have two classes, Versita and Setosa, and this is the line that we have tuned.
You selected one, -1 to 0.5.
Yeah, manually selected these values. And then we have the chart also. We have this one. I couldn't manage to change the colors, but this is kind of the diagram that you have showed in previous Perceptron part.
Yes. So we have the decision line plot in two ways. This is very good. So now, can you please, now you defined the omega by yourself. Can you apply Perceptron learning group?
No, I didn't.
This is the next step. So
Okay.
just, yeah. So please, we will have other presentations quickly in 4 minutes, and after that, you will go back to implement Perceptron learning group. Perceptron learning group, we will work with data, correct? So we just need to adjust omega. We need to initialize weights and bias with small random values or zeros, for example. And we need to calculate error, and we need to calculate delta omega. Delta omega will be eta multiplied by error multiplied by the input. Right? So now you have delta omega, you update omega. So it will be 3 lines of code.
Yeah.
But you need to put it in a for loop
Yes.
because you need to do it for each example, and you need to repeat this a number of times. So yeah, thank you very much. Can we go to a next group, please? Another group.
Yes, I can hear.
Yes, please.
Is it visible?
Yeah, visible. Very good.
Okay.
So now you got it. You got it
This-
from okay, two categorical. Very good.
These were just our initial data with all three type of
Three classes. Yes. So we selected Setosa because we have two classes here are overlapped, right? So
Yes,
it will be
and
complex.
and there are three type of floors: Setosa, Virginic, and so this is the representation of those three.
I mean, we cannot use blue and the green because blue and the green are overlapped, right?
Yes, correct.
Yes.
And then
So
I tried to calculate the error using predict, but there was some problem with the variable pred. I did not try to find out how to resolve that function. So
which function?
it was something like to calculate the error.
Yes. So
Well,
the
yeah.
the error, in fact, it's a t minus y. It's target value minus prediction,
Oh, okay.
right? So where is it here in this?
I just removed that statement because it was creating error in entire code. So probably I will
Okay.
do it later. So as far as this line is concerned, this is the line. We
Okay.
mentioned learning epochs 1000 instead of 100.
But he used you use the perceptron. You wrote this
Yes.
code, or this is your
I
function,
use-
or
I use actually Perceptron.
you used a function called the perceptron,
Yes.
and it's from
Here it is the function.
you wrote it. Okay.
Yeah, yeah.
So can you go step by step to it, please? Just relax
Okay.
to the perceptron. So can you go to your implementation of perceptron?
Here is the implementation of Perceptron.
Yeah. So first we need to initialize it. We initialize learning rate to just a small value, right? And we initialize weights to zeros, correct?
Yes.
And
actually.
yeah, and of course you are including maybe bias in weights, because you number of inputs plus one. Number of inputs plus one, it means you also
Because
initialize
if
the
it will
bias.
be, if somehow it will be 0, then ultimately +1 will be considered.
Okay, very good. And after that, you define this prediction. If you need to predict, so you need to calculate output. So it will be omega multiplied by weights plus
Yes.
bias.
Yes, actually I was
Uh,
issue with this training error and I removed that statement. I tried to calculate it, but it was creating some errors. So
mhm,
this is the output function. It's a
good.
activation function 1 in case it is greater than 0, otherwise it will be minus
Mhm.
for any other class.
Yeah.
So
But remember, you selected here 1 and the -1. So you selected the symmetric activation function. So can you go back to the dataset? Because
Uh,
when you select labels, did you use the function called the two categorical, correct?
yes, so this is actually the actual data set representation. I
Mhm.
shipped with 150 and 4.
Mhm. Yes.
One and
This is X, but just remember here Y, it's one vector, one column.
yeah, this is one vector Y. I have printed
and
it.
yeah, and if you need to replace Setosa and Virginica, for example, it should be replaced by 1 and -1. Just remember, not by 1 and 0. So just remember,
Okay,
because here you used the activation function 1 and the -1, right?
Yeah. Regarding the training, I added these 3 arguments. One is 3, and this is
Mhm.
again the training loop to collect the error. So,
Yeah, but just remember here, you don't need to adjust weights okay, you need to do it in 2 lines because we need
because
to.
I was trying to adjust the weights based on the error. If the error is
Yes.
high, then they will try to convert high level of weights, but it was not actually worked in my case.
Mhm.
So
Yeah, it should work. Plotting the decision line. So okay, very good. Slope, intercept.
these are just for 2 features for now, which are the basic.
Okay, very good, very good. Yes, this is very good. So just try to implement the training, try to test the training part. So the training part, it's implementing here perceptron learning rule. You are using perceptron learning rule. So try to test it.
Okay.
Yeah. So the next step will be testing this one. So when you are plotting, why is it looks like? Is there any problem here?
No, actually, it
function?
was initial without any boundary. So it is
Mhm.
a real plotting, which I
Okay.
handled.
Okay, very good. So now, but you have the weights you
Because I
defined
was
as
not understanding this data initially. I normally
Mhm.
do on a text, and after that text, I convert those text into numerical vectors using vectorization. These are actually already in feature form. So
Okay.
I
So
was trying
now,
to,
please try to implement this perceptron learning rule. It is in your code. You just need to do it.
okay.
Yes, thank you. And next group, please. Third group. Can we have the third group, please?
Andres, maybe you can show ours.
Yeah, give me a sec. I mean, what we did was so we found a decision line
Mhm.
based on some trial error values we tried to
Okay.
pick
Very good.
over here. So we
Mhm.
managed to separate the Setosa from a physical one,
Mhm.
but the trading loop still we need to
Yeah, you have
implement.
X. Yeah, because you have X1. This is okay, but X2, it's not. Okay, minus omega 1 divided by omega 2. What is omega 1 and omega 2? I don't know. Multiplied by X1 minus B. Yes, this one should be fine, right?
Mhm.
I mean,
we pick these values manually, so there's no training loop involved.
Yes. Now you need to implement perceptron learning rule.
Exactly.
So similar to the last example, you need to write your perceptron function, for example, one for going forward for calculating the predictions, and after that you will do the training, updating weights. So you need to subtract predictions from target value, calculate error, use perceptron learning rule, calculate delta omega equal learning rate multiplied by input multiplied by error multiplied by input, and just repeat it several times, and that is it. You should get something similar to those numbers, in fact. So keep that part as it is now, because you got those numbers by trial and error, for example, or by experience. Now you need to implement perceptron learning rule and compare those numbers. Can you get the same number? Right? Can we get better accuracy or something? Also, try to calculate the accuracy, please, of this model. Can you calculate accuracy?
Yeah, that's output within minus input.
Yeah. I mean, we do predictions. We subtract the predictions from, we calculate the error. So just maybe it could be mean square error, or it could be number of cases where target not equal to. So the prediction error, it will be number of cases where the target not equal to the prediction, right? So count those cases and find the prediction error or accuracy, for example. Yeah, very good. So please, next step is to implement PLR.
Yes.
Yeah, thank you. So last group, please, because we have only 4 groups. We still.
I can
Really?
probably share, but
Yes.
we had approximately the same as the last group here.
Okay, very good. Yes.
We didn't get to the chose these manually and just looked at how it would be in the plot and ended up at here.
Okay, so now can you start implementing perceptron learning rule?
Yes, that would be the next step, but I'm not. I need to read a bit more probably on how to execute that exactly.
Okay, I will just share my screen and I will show you how I did it, because maybe you can do it in much better way also, right? So so as you can see here, yes. So I did in fact similar to Ihtisham. So Ihtisham, he wrote a perceptron class called perceptron, and he initialized he just initialized, he selected number of epochs, he selected the learning rate, initialized it, and initialized the weights and the training error. And after that, we will have a function for calculating to predict. So you need to predict to calculate predictions. And once you have those predictions, you need to train your model. And in the training, you need to train it for number of iterations. Those number of iterations, we call it number of epochs, because I need to train my model for 10 epochs or 10 iterations, for example. In each iteration, we use the whole data set. So in each iteration, we will have another for loop where we can go through the whole set of test set, right? I will not call the whole data set, but just the training set, sorry, the training set. So here, I have another function called the train, and the input to this one will be my object, correct? And the training input and the training labels. So the input will be X and the T, for example, target value and X. And we will run this one for number of epochs, correct? And in each epoch, we need to calculate maybe prediction error, right? So we need to initialize error in each epoch because I need to plot it at the end. So for all inputs, for all training inputs and the training labels, we calculate prediction. So prediction equals self.predict. So I will provide input to my model and it will calculate prediction. So I will start with the first input, right? I will start with the first input data point, and I will get prediction. So the first input here, it will be maybe X1 and X2, and I will get the first prediction, which is maybe Y1 or something. And after that, I will apply this rule. This one, it's perceptron learning rule. And in this perceptron learning rule, it's very easy. It's just omega equal omega plus learning rate multiplied by error multiplied by input, which is X. That is it. So it's just one line. one line for omega, one line for B. B equal B or B, so sorry, bias plus eta multiplied by error multiplied by +1. Just to, I mean, if you want to combine it in one line, it's okay, no problem. And after that, you need to just calculate prediction error. So error equal error plus maybe error or label minus prediction, right? This is my error. So I need to calculate the error, prediction error in each epoch because I need to visualize it. So I need at the end to plot a graph like this one, with this as number of epoch on x-axis, and on y-axis we will have this prediction error, for example. So in iteration number 1, the error was this amount, and iteration number 2 should decrease a little bit because we are in learning process. In iteration number 3, it will decrease, and so on. So we need to see a graph like this one. We call it maybe prediction error or loss function or something. So you will calculate this error value, error equal error plus. I mean, this error don't mean it's not correct, in fact, because we are not appending here, right? So this error value should be just a single value. So don't need to write here error dot mean because this one is wrong. It's just error, right? Because we're just adding it. Maybe if it will be just the error in each epoch, right? If you want to take the average, maybe you need to store this one in. Maybe you can just write error divided by number of data points, something like if you want to plot average error. So now you have the function in front of you. So please try to make those changes so we can implement perceptron learning rule and compare between the weights after finishing the training, maybe for 20 epoch, for example. Try to so now I will train my model here for 10 epoch. You see, number of inputs equal 2 because I will use only 2 inputs because I want to we want to plot it into dimensional space. So we'll just use 2 inputs, x1 and x2. We will train the model for 10 iterations, and learning rate will be this 0.1, right? And after that, you need to plot. After doing this, you will get this b dot error. I mean, training error here. Just to plot the training error against number of epochs. So so just try to train your model. Plot this graph first, and after that, plot also the decision line, the new decision line, because you will get a decision line. So try to plot the decision line and try to plot this training error. Is it okay? We can also take maybe 10 minutes, right? I guess you can go back to the same. Is it possible to go back to the same? I can move you again to the same room. Is it okay? You can go back to the same room, right? Move to no room, room number 1. Okay. Is it possible to open all rooms one more time? So just to go back to your room and try to implement that part. We will use 10 minutes. We will finish at 12:30, so I will not disturb your time today. So just to try to implement this perceptron learning rule, please. Hello. Should we get people back from rooms? Hello, everybody. Are you ready to come back? Hello? Hello, guys. Hello, everyone. So can we take, also see progress in each group? If you didn't finish, you can go back to, you can work together again. But because I noticed that some people, they went already, so I guess it's nice to have some presentations from you so people can go to other stuff if they have meetings or courses. So can we take one presentation from one group, please?
I can start if you want. Can you hear me?
Yeah. Can we take one presentation, please?
Yeah, I can share it.
Can you share? I need to stop sharing, or?
Yeah.
Okay, very good.
Like there is a small error that I'm trying to figure out, but I think the idea is correct.
Okay, so you will train it for 10 epoch.
Yeah, I will train it for.
You are doing it. You are doing it for the whole batch,
Yeah,
right?
for
Not
the
example
whole-
by example, correct?
For the whole batch, I'm using, like I didn't separate for training or testing. I'm using whole data. So we have the error term here, which is the learning rate times the target minus prediction times the settlement and the petalent. And this is our error. And then we add the error into define a new.
Because in perceptron learning rule, we do it example by example because the rule here it's x nu equal omega nu equal omega plus eta multiplied by error multiplied by n dot.
Yes.
Oh, you did that already. Okay.
Yeah, I have already did it, and this is for the.
So you don't need to call it error. You just call it delta omega, right? This is not error. It's delta omega.
And we update the weights here, and we have the new weights at the end. And here I combine the bias and the error. This is for the bias part, and this is for the weight part. I made them interesting of.
And you got error message, right?
Yeah, I think it's about the plot part or the prediction of y part. I couldn't manage to fix it, but it should work. I mean, the idea is correct.
Okay, this is very good. So perceptron learning rule, it's very smart because it helps us to train the perceptron from data. Because the most important, our models, we call it data-driven, right? Data-driven. So it should be trained by data, not by hand. So just to try to train it by trial and error, just to get an idea what is going on. But in reality, we need to work with data. We cannot work with, we cannot decide it by ourselves or by trial and error. We need to do this by from the data. So it's learning from data. We can call it learning from data. Yes, thank you very much. Can we get another group, please?
I can share what we worked on.
Yes. And you can, after this presentation, you can work together. Maybe if you need more 10 minutes or something to do it, it will be nice.
Yeah, it was a bit fast. We were still, we implemented your example that you showed in the slide.
Okay.
So
Okay.
we try to work with your class definition with the perceptron. So we define it over here and at the beginning. And trying to reconstruct the values over there.
Yes,
over here,
the values. Okay, train.
Over here, we're calling the perceptron and trying to train the data. But as you can see, we're in the middle of debugging still.
Okay. So just to take your time later on, no problem. You can just we finish those presentation. After that, you can continue working with your group until 12:30 or as far as you want. Yeah.
Yes.
Okay. So thank you very much. Thanks. So is the third group, please?
I can probably go. Let me share. So I too took the liberty of using your perceptron class, and I changed the activation here to 1 and 0. Pretty much inserting the columns I'm interested in, which was selected in the previous task. and doing the training and doing the plotting. And I think this looks a bit
Yeah, because
funny.
maybe just as a calculation. I mean, the calculation of error is because it's zeros. It's a zero, which is good. Maybe by chance you got. It's by hitting.
Got
Maybe you
lucky.
are hitting the best values, but you can print the values. So you can print the values to see how it look like. So the perceptron parameters omega 1, omega 2, and it's you defined it b something. I mean weights and yes, b dot weights, right? B dot weights. Yeah, those numbers. So
yeah. Anyways, so that's that, and then
yeah. In fact, also it would be nice if you can plot omega 1 and omega 2 and the bias over number of epochs to see how they will progress, because we are starting from random values. We initialize the weights and the bias with very small random values, right? So are starting from random values, and over each epoch you can store also the weights and the bias and the plot it. It would be nice. Here in this example, we are appending error, correct? So you can also the same way you can store also values for omega 1 and omega 2 and the bias to plot it to see how it look like, because we are starting from initial values, and it will. So yes, as a matrix. Yes. So yes, very good, very good. So in this case, after each epoch, we will store it. We will store those. This is very good. And you can plot also those values. It will give you some. It will show you that okay, the training process is working.
Let's see here. Just select. Oops, can probably do this. Yes, of course. So this is gonna be oops, yeah. Could just iterate and scatter. Should I do that?
Scatter plot? No, it should be just line, because right? It should be line. This
yes.
is correct. Adjusted.
Yeah. Because I have all of these different weights in here now. I guess I'll just select one of the weights.
The first one. Yes. Yeah. As you can see, you are starting from some zero value, and it goes down. But you can see that at some point it's zeros all time. So which means maybe we have some problem. It's not updated, right? So this is very good. So I mean, plotting also the weights will be nice, because there is in fact a website called weights and bias. You can connect it to your model, deep learning model, for example, or feed forward a neural network, and it will be plotting all those weights and bias for you. Sometimes it's nice to look into it. Yeah, thank you very much. Thanks. Yeah, can we go to the maybe last group, because we have 4 groups. Do we have any people from 4th group, or it's only 3 groups? Only 3 groups, right? Okay, so in this case, just please, you can go back. I can keep, I mean, the this link opened. So if you want to work with your group until 12:30, for example, if you want. Yes, and today I will upload my slides to Blackboard, and also I will put the link for this YouTube link for lecture, the first part, and we will meet again next week. Yeah. Thank you very much.
Thank you.
Thanks for today, and have
Goodbye.
a nice weekend. Bye bye. Bye bye.
Thanks for the lecture. Bye-bye.
Bye.
Thank you. Thank you. Bye bye.
Have a nice weekend. Bye.
The same to you. Thank you.
Bye.
Bye bye. Bye bye. Thanks.
Andre and Marcus, do you want to continue, or should we?
Yeah, I'll be up for just having a look at how we can fix
Yeah.
our code just to get it running a bit.
That would be nice. Yeah, you can share your screen, and then we can just work on it.
Yeah, I mean, I sent the codes to you as well, so you can in parallel you can have a look at it too.
Yeah, that's true.
You have to forgive my Python skills. I'm not too experienced within Python, so
No worries.
so let's see. We were here. Not sure what the problem is here. Too many indices for an array, one-dimensional, but two were indexed. F2 here.
Yeah, let's see. Yeah. Array is one-dimensional, but two were indexed. Can you try to? It seems like if you number of inputs, we're gonna have two inputs, right? To 100, X is now there, and then you are. If you try to just plot X, what you're inserting there into training inputs in p.train, no, at the lowest. Yeah, just plot X. Yeah, or sorry, just print the array. That was my intention to say. And then I think you can just copy.
This is the entire array,
Yeah,
and if you
yeah.
do, this is what we
Like that. That was the intention.
aim to do, which is the first two columns.
Yeah. But if you go down and you see the printed shape, we get 2 by and if you go a bit further down there, yeah, no, sorry, it's I need to
You can also take control, I think.
again.
So we can share. Yeah.
Where? Let's see. Am I able to take control? View options. Request remote control. There you know. Nice. So these. Okay, so it just zips them together, and that's the shape. And then it is on this line. It
On iris data there, should it be a square? X equals iris data square.
Yeah, I think it's how we find the data set.
Okay, yeah, okay, I saw
I
already
think that might be the problem.
Yeah. Wait, where?
If you go, let's go up here. I think that might be here.
Different print X. Yeah, of course we are redefining.
I think that might be.
And we're just gonna have the two first ones, or like that. This is the correct one, right?
Mm-hmm. Yeah.
And how about Y?
Might not be the case actually, because we, if you go to scatter, you see we use the second and the third column to train data actually. So we don't. So taking the first two
Yeah.
columns is not so it's not correct for training data. I see.
Yeah, but regardless, it's not. It doesn't
No,
interpret
true.
it as the wrong data. It's just the shape that it's.
That's not working with. I agree.
Predictions in this. Have I not done this correctly? Inputs.
Wait. This is the wrong.
Text. Number weights.
Let's see.
Can you print the weight? It says self.weight 1 in the
Where?
predict here in this line. Just weights. Oh, that's a new bit. Wait, let's see. Just want to see, yeah,
That's correct,
Ah.
right? So
yeah, but do we need to just transpose it?
no, now it's
Huh?
99.
Yeah, yeah. Why?
We just showed it. This other guy, he had exactly this, but then he used it to call one and call two columns.
Uh,
Weekends we just do call.
yeah,
See if that works. Like,
also same dimensionality issue.
I figured maybe it might be something with how this array is formed, but it's not liking this in any case. Yeah.
Yeah, but this is an array in array, and
Yeah.
the training for epochs for inputs and labels in training inputs. Then it takes the first element, send it to prediction.
I'm just fumbling around
yes.
right now.
Oh yeah, I have one. Sorry if I took control. If we try, because now here there are two. This is an array with two elements, right? But this is an array of. Could you just try to print this, for example, when we initiate it? Just to see.
And just remove this stuff. Oh, sorry.
Yeah.
And then just replace it with X again. X.
Why didn't it print anything?
You still have the screenshot from the slides?
Ah, okay.
Because it could be over, they just copied something wrong over, maybe missed something. I suspect might be that.
Yes. I do have it. It's the same.
No, I have it as well. Good. Okay. Because it's from thing.
No, that's the issue.
Yeah, exactly. Yeah. So now it should work. But then we need to fix what is it? That the right trading data is used instead of the first two columns.
Yeah. But it still doesn't. But still this issue, one dimensional, but two were indexed. Still?
Mm-hmm.
Still? That's the problem there, of course. In the print function.
I think it's self.weight must be the case. Self.weight. It's
Yeah,
weight.
this one. Let's try again.
Yeah, okay.
Ooh.
This looks like it's printing a
Looks
lot,
like it's
20
running.
times.
Yeah. Okay. Let's remove the debugging prints. This one. And this one. Oh, that was a. Oh, like that.
Hmm? Yeah.
Should we then log some stuff? Maybe self dot
Yeah, weight.
error trajectory, for example.
Yeah.
No, wait to
and,
try to. Yeah.
Yeah. And plot the weights.
Dot append, and that was the weights, and that will be like that. We can just do
But
like.
yeah, exactly.
Agree?
Mm-hmm.
Or so then
Yeah.
we have a log for the weight trajectories, right? And that will be 2 values, no, 3.
3 values, yeah.
So that will be a list of lists with 3 elements in each.
And how are they stacked? And now we just need the yeah, exactly.
The
Over
correct
there.
ones.
And that's from 2, 1 and 1. Just add a 1, yeah. I think it should be good.
And to the third, is that correct?
I think it's just what did we use here? 1 and 2 only. So I think it's this.
But won't that be only one column? I think, yeah.
Okay. Yeah, okay, then it's
Oh, not appends. It's append. Dang, that's a lot of tiny issues that.
okay, nice. So now we can do plot, and then it's How do you obtain some?
Yeah, the error, for example.
Yeah. Do you? It's p dot, I suppose.
P dot error. Isn't that the training error? Yeah, that's probably it.
Training error. Yeah, and this is automatically 20 arrays long. Yeah. Okay.
Yeah.
Why does it go from 0 to?
No, it goes past 17.5, so it's probably 20.
Yeah.
So that's okay.
Okay. Then we can also do
So
the
then it's
plot.
in
P dot and then weight trajectory. Do you know if you can plot? I mean, right now it contains three
I think
values,
maybe
right?
try it
See
should
what
just
works. Okay. Doesn't like it. How do you open a new figure?
I thought it was supposed to be able to plot a list of lists. Plot
Always.
list.
I can also just open up a new.
They don't change. Is that?
That's what it looks like, but the error changes.
Yeah. So then there's something fishy with the plotting. If you just sort of plot the list.
What do you mean, the list from all the weights?
Weights, yeah, down there. Just
Yeah, I suppose.
not plotted, just printed. That's no.
Let me transpose it like
But
this.
okay, they actually don't change. You see.
Yeah, or they are not stored correctly. That can also be the case.
Yeah, that can also be the case. Yeah.
Yeah.
Yeah, it's not in the correct training loop. Like, yeah, it is.
For here, it's in the epochs. Okay, this epochs. So it's right here. It updates every time to find an error.
So, this is that's the delta times the input. So this is the new weight. And that is input by input.
Yeah, we just plot the weights here. Print.
Yeah.
See if this gives any changes.
Yeah, they change.
They change, so it's storing issue. I mean, yeah.
Right? Okay, if you go up, maybe it's the input to do the, that's the reason.
I think that it appends it stacks it horizontally. It should be below each other.
Well, did you did you plotted the self dot weight, right? If you just control
Yeah.
that's what you did now.
Here. Over here.
Yeah.
Oh, you wanna plot them here still
That's
like this.
self
So I
dot
print.
weight.
Like this is a 1x3
Mhm.
array, but over here I'm not sure whether if you append it over there if it's what your array then will look like. If it's still a 1 by if you append it by the 3 values every time. See my point? If you get something if it's still a 1 by if it adds 3 values to the same array every time.
Yeah, if
Not
you see
vertical
if you
stuff.
scroll down, there here.
Yeah.
This is P dot. This is a trajectory. So there is 3 values. And there's 3 values. But why is that not the same as these? Should I...
Yeah, just towards the very last epoch.
Yeah.
Interesting.
Because the epoch is defined there.
Yeah.
Well, yeah. We got the error at
Complicated.
least.
Yeah.
It
Yeah.
might be something to do with the numpy, but because this is a numpy array. Why it only takes the last one, that is for me a yeah. Maybe I need to have some breakfast.
Yeah. Yeah, I gotta go myself.
Yeah,
Yeah.
good. In any case, we got it running. I think that's the important thing.
Yeah.
Yeah. Yeah.
Yes.
Yes. Okay.
Good. I will
Nice.
share this with you again.
Yeah.
So,
Yep. Thank you.
you will
Thank
have
you.
it too. Good.
See you next time.
See ya.
Yes. Bye-bye.
Bye.
Bye.